Hello, and welcome to the Drowsy Professor. I'm so glad you're here tonight, ready to embark on a gentle journey through time to the ancient oceans where remarkable creatures called trilobites once lived. As you settle in, let me know where in the world and at what time you're watching. Now, get comfortable. Adjust your pillows, pull up your blankets, and take a slow, deep breath. Let the stresses of the day begin to melt away as we prepare to drift back through hundreds of millions of years to explore the peaceful, primordial seas. Take another breath and let's begin. Imagine, if you will, closing your eyes and feeling yourself gently floating backward through time. The modern world with its bustling cities and glowing screens fades away like a distant memory. You drift past centuries, then millennia, then millions upon millions of years, until you find yourself suspended above an ancient Earth that looks nothing like the world you know today. The continents below you are arranged in unfamiliar patterns, clustered together in ways that would seem strange to modern eyes. Where you might expect to see the familiar outlines of the lands you know, instead there are vast, warm, shallow seas stretching endlessly in every direction. These are not the deep, cold oceans of today, but something altogether different. Something more like an enormous, sun-warmed lagoon that covers much of the planet. As you descend gently toward these ancient waters, you notice immediately how different the light appears. The sun shines down through a crystal-clear atmosphere, unmarked by the pollution or even the familiar clouds that you're used to seeing. The water below reflects this pure light in shimmering patterns that dance and ripple across the surface, creating an ever-changing mosaic of gold and blue and green. The temperature of the air around you is warm and humid, like a permanent late spring day. There's no ice anywhere on this ancient Earth. No polar ice caps, no frozen tundra, no snow-capped mountains. Instead, the entire planet basks in a greenhouse warmth that keeps even the poles comfortable and mild. The sea beneath you radiates this warmth upward, creating gentle thermal currents that lift you softly as you float above its surface. As you draw closer to the water, you begin to notice something remarkable about its clarity. Unlike the often murky coastal waters of the modern world, these ancient seas are so transparent that you can see far down into their depths. The water has an almost crystalline quality, tinted with the faintest hint of blue-green, like looking through a perfectly polished gemstone. There are no rivers carrying sediment from vast forests or grasslands, because those forests and grasslands don't exist yet. The land is mostly bare rock and simple microbial mats, so the runoff into these seas is clean and clear. The very chemistry of these waters is different from anything you might experience today. The oxygen levels are lower, giving the atmosphere a thinner quality, while other gases mix in different proportions. This creates a unique environment that shimmers with possibility, where life is experimenting with forms and functions that have never existed before and may never exist again. Now, as you gently break the surface of this ancient sea, you feel the warm water embrace you like a comfortable bath. The temperature is perfect, not too warm, not too cool. Just the right temperature to make you want to sink deeper and relax completely. The water has a silky quality against your skin, mineral-rich and soothing, like the most luxurious spa treatment you can imagine. As you float here on the surface, looking down into the depths, you begin to realize that you're not alone in these waters. Far below you, barely visible at first, there are movements in the clear depths, shapes that glide and scuttle and drift with the gentle currents. These are not the fish and dolphins and whales that you might expect to see in a modern ocean. Instead, they are creatures that seem almost alien, yet strangely beautiful in their unfamiliarity. The seafloor below spreads out like an underwater landscape of gentle hills and valleys. It's covered not with sand or mud, but with a thin layer of the finest sediment, so delicate that the slightest current stirs it into graceful clouds that catch and scatter the sunlight filtering down from above. In some places, the bottom is dotted with strange, tower-like structures that rise up from the depths. These are stromatolites, Massive colonies of bacteria that have been slowly building their calcium carbonate homes for millions of years. Between these bacterial towers, the seafloor undulates in soft, rolling patterns. Here and there, you can see what look like underwater gardens, but instead of plants, these are colonies of simple animals that wave gently in the current like underwater flowers. Some are shaped like fans, others like delicate brushes, and still others like tiny trees with branching arms that sway back and forth in the eternal submarine breeze. The lighting in this underwater world has a dreamlike quality. The sun, filtered through layers of crystal clear water, creates shifting patterns of brightness and shadow that move constantly across the seafloor. Sometimes a cloud passes overhead, and the entire underwater landscape dims slightly, creating an even more peaceful twilight atmosphere. Then the cloud moves on, and the golden light returns, illuminating the ancient seascape in warm, honey-colored tones. As you float here, suspended between the surface and the depths, you become aware of the profound silence of this ancient world. There are no whale songs echoing through the water, no schools of fish creating rushing sounds as they move in unison. Instead, there's only the gentlest whisper of water moving past your ears, and perhaps the very faint crackling sound of the bacterial colonies far below as they continue their ancient work of building and growing. This silence isn't empty or lonely, it's full of potential. It's the silence of a world that's still young, still discovering what's possible. Every drop of water around you is teeming with microscopic life, invisible to your eyes, but busy with the work of living and reproducing and evolving. These tiny organisms are the foundation of everything that will come later, the base of a food web that's just beginning to explore the possibilities of complexity. The water itself tells a story as you move through it. Its warmth speaks of a planet where the climate is stable and nurturing. Its clarity tells of a world not yet shaped by the massive geological processes that will later create mountain ranges and deep ocean basins. Its mineral-rich taste, if you were to sample it, would reveal the chemistry of an Earth that's still in its youth, still experimenting with the ingredients of life. As you drift deeper into these primordial waters, you begin to notice subtle variations in the seafloor below. In some areas, the bottom is covered with what looks like a soft, velvety carpet. This is a microbial mat, millions upon millions of tiny bacteria living together in a community that forms the foundation of life in these ancient seas. These mats come in various colors, from deep green to rust red to purple, creating an underwater patchwork that shifts and changes as different types of bacteria dominate different areas. The microbial mats aren't static. They're alive and growing, constantly filtering nutrients from the water and slowly building up the seafloor beneath them. As you watch, you might notice tiny bubbles rising from their surface. Oxygen being produced by photosynthetic bacteria, one of the first sources of the gas that will eventually transform the Earth's atmosphere and make more complex life possible. In the spaces between these bacterial gardens, the seafloor reveals its underlying structure. Sometimes it's made of limestone, built up over millions of years from the shells and skeletons of countless microscopic organisms. Other times it's composed of fine sand or silt, deposited grain by the gentle currents that flow across this underwater landscape. The texture varies from place to place, creating a seafloor that's as diverse and interesting as any terrestrial landscape. Here and there, you notice small mounds rising from the bottom, the homes and burrows of creatures that live within the sediment itself. These aren't the complex burrow systems that will be created by later animals, but simple tubes and chambers carved out by some of the first animals to discover that there's safety and food to be found beneath the seafloor surface. The water column itself is alive with movement, though it's so subtle that you have to watch carefully to notice it. Tiny particles drift past like underwater snow, and occasionally you catch sight of something larger. A jellyfish-like creature pulsing slowly through the water, or a small, swimming organism that darts past and then disappears into the blue distance. The temperature gradients in the water create gentle mixing patterns that you can sometimes see when particles or slightly different colored water reveal the currents. Warm water rises from the sun-heated shallows, while cooler water sinks slowly toward the depths, creating a constant, gentle circulation that brings nutrients and oxygen to every part of this underwater realm. As you continue to explore this ancient seascape, you begin to appreciate the incredible antiquity of the world around you. These waters have been here for millions of years, slowly warming and cooling with the seasons, gradually changing as the planet itself evolves. The creatures living here are the descendants of some of the very first complex life forms on Earth, and they're also the ancestors of virtually everything that will come later. There's something deeply peaceful about floating in these ancient seas, surrounded by life forms that have perfected the art of simple existence. They don't rush or hurry or compete in the frantic ways that modern life often seems to demand. Instead, they follow the slow rhythms of geological time, growing and reproducing and evolving at a pace that's measured in millions of years rather than minutes or hours or days. The water around you holds dissolved minerals that sparkle occasionally when they catch the light just right. These are the raw materials that the organisms here use to build their shells and skeletons and homes. Calcium and silicon, phosphorus and trace metals, all dissolved in perfect solution, waiting to be incorporated into living structures by the creatures that call these waters home. As you float here in this ancient sea, you can feel the gentle pressure of the water supporting your body completely. Every muscle can relax as the buoyancy removes all weight and stress from your limbs. The water's warmth penetrates deep into your tissues, soothing away any tension or discomfort. This is a world where gravity seems less important, where the harsh edges of terrestrial existence are softened by the forgiving embrace of the sea. The horizon in every direction is nothing but water meeting sky, an endless expanse of blue-green sea stretching to the limits of vision. There are no continents visible from here, no mountains or coastlines to break the perfect curve of the Earth's surface. You are in the middle of an ocean world, a planet that's mostly water, mostly life, mostly potential. Time moves differently here in the ancient seas. Minutes stretch into hours, hours into days, and days into seasons. But it all feels like one continuous, peaceful moment. The sun moves across the sky in its daily arc, creating shifting patterns of light and shadow in the water below. But there's no sense of urgency, no feeling that time is running out or that anything important is being missed. This is a world where patience is not just a virtue, but a necessity. Evolution works slowly here, trying out new ideas over millions of years, keeping what works and discarding what doesn't. The creatures you see around you are the result of this slow, careful process of experimentation and refinement. They represent life's first attempts at complexity, its earliest explorations of what it means to be a multicellular organism in a vast and nurturing sea. As you drift deeper into these ancient waters, you begin to understand that you're not just visiting another place. You're visiting another time, a time when the Earth was young and the possibilities seemed endless. This is the world that existed before the familiar forms of life, before forests and flowers and birds and mammals. This is the primordial sea from which everything later emerged, the womb of all complex life on Earth. The feeling of floating here is almost like returning home to a place you never knew you'd left. There's something in the rhythm of the gentle currents, something in the quality of the light filtering down from above that feels deeply familiar at a cellular level. Perhaps it's because all life, including human life, carries within it the memory of these ancient seas, the chemical signature of this primordial birthplace. And it's in these warm, nurturing waters, among the microbial mats and simple animals of this ancient world, that we're about to encounter some of the most remarkable creatures that ever lived on Earth. They haven't appeared yet in our journey through these Cambrian seas, but they're coming. Soon, the seafloor below will begin to stir with new kinds of movement, and the age of the Trilobites will begin. But for now, just float here in this peaceful, ancient sea. Feel the warm water supporting you. See the gentle light filtering down from above, and let yourself relax completely in this underwater cradle of life. The story of the Trilobites is about to begin, but like all the best stories, it starts slowly, with the setting of a scene and the building of a world that will soon be home to some of the most amazing creatures that ever lived. Breathe deeply. Let the warm, ancient waters surround you completely, and prepare to witness the emergence of life forms that ruled the seafloor for longer than any other group of complex animals in Earth's history. The Trilobites are coming, and their story is about to unfold in the gentle depths of these primordial seas. As you continue floating in these ancient waters, suspended in the warm embrace of the Cambrian Sea, you begin to notice something extraordinary happening in the depths below you. It's subtle at first, so gentle that you might mistake it for the play of light and shadow on the seafloor. But as you watch more carefully, focusing your attention on the microbial mats and bacterial gardens that carpet the bottom, you realize that something remarkable is taking place. The change begins so slowly that it's almost imperceptible. In certain areas of the seafloor, where the microbial mats have grown particularly thick and rich, small disturbances appear in the smooth surface. These aren't the random movements caused by gentle currents, but something more purposeful, more deliberate. It's as if the seafloor itself is beginning to wake up after eons of quiet bacterial existence. If you drift closer to the bottom, following one of the gentle thermal currents that carry you downward through the crystal clear water, you can see these disturbances more clearly. They appear as tiny mounds and depressions in the microbial surface, patterns that suggest something is moving beneath the bacterial carpet. The movements are slow and patient, following rhythms that seem to match the ancient pace of this underwater world. These first stirrings represent one of the most significant moments in the history of life on Earth, though they unfold with such quiet grace that their importance might not be immediately apparent. What you're witnessing is the emergence of complex, multicellular life from the simple bacterial communities that have dominated the seas for billions of years. This is the beginning of what scientists call the Cambrian explosion, though explosion is perhaps too violent a word for such a gentle and gradual transformation. The water around you seems to shimmer with anticipation, as if the sea itself knows that something momentous is about to occur. The temperature remains perfectly warm and comfortable, but there's a new quality to the light filtering down from above, a brightness that seems to highlight every detail of the seafloor with crystalline clarity. The very chemistry of the water is changing in subtle ways, becoming richer in the dissolved minerals and nutrients that will fuel the growth of these new forms of life. As you watch, mesmerized by the slow dance of disturbance and growth on the seafloor below, you begin to see the first actual creatures emerging from their hiding places within the microbial mats. They're unlike anything that exists in the modern world, yet there's something hauntingly familiar about them, as if they represent the fulfillment of possibilities that have been waiting patiently for millions of years to be expressed. The first creatures to appear are small and simple, barely larger than your fingernail, but they move with a purpose and coordination that immediately sets them apart from the passive bacterial colonies around them. They have bodies that are soft and flexible, able to contract and expand as they glide across the seafloor or burrow gently into the sediment beneath the microbial mats. Some of these early animals look like tiny, flattened discs with radial patterns etched into their surfaces. They glide across the bacterial mats like living coins, their circular bodies pulsing gently as they move. Others resemble small, segmented worms, their bodies dividing into distinct sections that work together in waves of coordinated movement. Still others look like microscopic jellyfish that have settled onto the seafloor, their bell-shaped bodies contracting rhythmically as they feed on the bacteria beneath them. The movements of these creatures create gentle currents in the water just above the seafloor, stirring up tiny particles that catch and scatter the filtered sunlight. As they glide and burrow and pulse their way across the bottom, They leave behind trails in the microbial mats, the first evidence of animal behavior preserved in the geological record. These trails wind and curve in graceful patterns, recording the ancient pathways of creatures that lived over 500 million years ago. What's most remarkable about these early animals is their apparent peacefulness. There's no sense of predation or competition in their movements, no frantic rushing or violent encounters. Instead, they seem to coexist harmoniously with each other and with the bacterial communities that provide their food. They move like gentle gardeners, tending their underwater crops, carefully harvesting the bacterial mats without destroying them, ensuring that their food source will continue to regenerate for future meals. The diversity of these early creatures is astounding, considering that complex life has only recently begun to experiment with multicellular organization. Each species has found its own way to make a living on the seafloor, its own approach to the challenges of being a complex organism in a simple world. Some specialize in gliding across the surface of the microbial mats, others in burrowing beneath them, and still others in filtering nutrients directly from the water column above. As you drift lower in the water, coming closer to this ancient seafloor community, you can observe the intricate details of how these creatures interact with their environment. The ones that glide across the surface move with a fluid grace that's hypnotic to watch. Their bodies seem to flow like liquid across the bacterial mats, conforming perfectly to every small hill and valley in the seafloor topography. They leave behind them trails of slightly disturbed sediment that slowly settle back into place, erasing the evidence of their passage like footprints in soft sand. The burrowing creatures work with patient persistence, their soft bodies perfectly adapted for moving through the sediment beneath the microbial surface. They don't dig in the aggressive way that modern animals might, but instead seem to flow through the sediment like water finding its way through porous rock. Their movements create networks of tiny tunnels and chambers in the seafloor, the first complex three-dimensional habitats ever constructed by animal activity. The water immediately above the seafloor shimmers with the constant, gentle disturbance created by all this quiet activity. Microscopic particles drift upward in lazy spirals, carried by the barely perceptible currents generated by the movements of hundreds of thousands of small creatures. The effect is like watching snow fall upward, a constant, gentle precipitation of tiny particles that catch the light and create ever-changing patterns of brightness and shadow. Temperature variations in the water become more complex as the seafloor comes alive with animal activity. The metabolism of all these creatures generates tiny amounts of heat, and their movements create microcurrents that mix the water in new ways. The result is a seafloor environment that's more dynamic and varied than the purely bacterial communities that preceded it, yet still maintains the peaceful, nurturing character that makes these ancient seas so conducive to the development of complex life. The bacterial communities themselves seem to respond positively to the presence of these early animals. Rather than being damaged or destroyed by the grazing and burrowing activities, the microbial mats appear to become more robust and diverse. The animals' waste products provide new nutrients for bacterial growth, while their movements help distribute bacteria to new areas of the seafloor. It's a perfect example of what will later be called symbiosis, different forms of life working together for mutual benefit. As days pass in this ancient underwater world, you begin to notice that the animals are not randomly distributed across the seafloor. Instead, they seem to prefer certain areas over others, creating concentrations of activity in the most favorable locations. Areas where the microbial mats are particularly thick and rich tend to attract larger numbers of creatures, while barren patches of sediment remain relatively empty. This spatial organization creates a landscape of life that changes constantly, but slowly, like a living map that redraws itself over the course of days and weeks. You can follow the migrations of different species as they move from area to area, always seeking the best feeding opportunities while avoiding overcrowding in any single location. It's a dance of ecological balance that's both complex and graceful, performed by creatures that are just beginning to learn the steps. The lighting conditions in this underwater world continue to play a crucial role in shaping the behavior of these early animals. During the brightest part of the day, when the sun's rays penetrate most deeply into the clear water, many of the creatures become more active, taking advantage of the energy provided by the photosynthetic bacteria in the microbial mats. As the light dims toward evening, activity levels decrease, and many animals retreat into the safety of their burrows or become more sedentary on the seafloor surface. This daily rhythm of activity and rest represents one of the first examples of circadian behavior in complex animals. The creatures are responding to the same daily cycle of light and darkness that affects life throughout the history of the planet, but they're doing so with nervous systems and sensory organs that are still in their earliest stages of development. Their responses are simple but effective, allowing them to synchronize their behavior with the rhythms of their environment. The water itself continues to provide the perfect medium for this early experimentation with complex life. Its warm temperature keeps metabolic processes running at optimal rates, while its rich mineral content provides all the raw materials needed for growth and reproduction. The gentle currents ensure that nutrients and oxygen are constantly circulated throughout the seafloor environment, while the crystal clear water allows sunlight to penetrate deep enough to power the photosynthetic bacteria that form the base of the food web. As you observe this ancient ecosystem in action, you begin to understand that you're witnessing something truly unprecedented in the history of life on Earth. For billions of years, life had been dominated by single-celled organisms that lived relatively independent existences. Now, for the first time, cells were beginning to work together in coordinated groups, creating organisms that were greater than the sum of their parts. The implications of this development are staggering, though they unfold so gradually that their full significance might not be immediately apparent. These early multicellular animals represent the first experiments in biological complexity, the first attempts to create organisms that could perform specialized functions and respond to their environment in sophisticated ways. They are the ancestors of every complex animal that will ever live, from the trilobites that will soon dominate these ancient seas to the human beings who will eventually study their fossilized remains. The evolutionary innovations taking place in these Cambrian seas are happening at a pace that's rapid by geological standards, but still slow enough to observe and appreciate in detail. New body plans are being tested, new ways of moving and feeding and reproducing are being explored, and new relationships between different organisms are being established. It's like watching the rough draft of complex life being written and rewritten in real time. Some of the creatures you observe seem to be experimenting with the development of hard parts, tiny mineral structures that provide support or protection for their soft bodies. These are the first tentative steps toward the development of shells and skeletons, innovations that will revolutionize the fossil record and allow paleontologists to study ancient life in unprecedented detail. For now, these hard parts are simple and small, but they represent the beginning of a trend that will eventually produce some of the most elaborate and beautiful structures in the natural world. The seafloor environment continues to evolve as more and more animals join the community. The burrow systems become more complex and interconnected, creating three-dimensional networks that extend deep into the sediment. The trails and tracks on the surface become more varied and numerous, recording an ever-increasing diversity of behaviors and movement patterns. The microbial mats themselves begin to show signs of adaptation to the presence of their animal neighbors, developing new strategies for growth and reproduction that take advantage of the changed conditions. As you float here in this ancient sea, watching the slow emergence of complex life, you can feel the profound significance of what you're witnessing. This is not just the appearance of new organisms, but the birth of entirely new ways of being alive. These creatures are pioneering concepts like coordinated movement, specialized body parts, and complex behavior that will eventually give rise to all the diversity of animal life that follows. The water around you seems to pulse with potential energy, as if every molecule is charged with the possibilities that are beginning to unfold on the seafloor below. The temperature remains perfectly comfortable, the pressure perfectly balanced, the chemical composition perfectly suited to support the delicate experiments in complexity that are taking place in every grain of sediment and every drop of seawater. Time continues to move at its ancient pace, allowing you to observe these changes without any sense of rushing or urgency. Days blend into weeks, weeks into months, and months into years, but the gradual transformation of the seafloor continues steadily, accumulating small changes that will eventually add up to revolutionary transformations in the nature of life itself. And still, the most remarkable changes are yet to come. The creatures you've been observing represent just the opening act in the great drama of the Cambrian explosion. Soon, the seafloor will witness the appearance of animals with features that seem almost impossibly advanced for such an early stage in the history of complex life. Animals with eyes that can see, with legs that can walk, with mouths that can bite and crush and filter. The age of the Trilobites is about to begin, and when it does, it will transform these peaceful bacterial gardens into something far more dynamic and diverse than anything the Earth has ever seen before. The transformation begins on what seems like any other peaceful day in these ancient Cambrian seas. You float in the warm, crystal-clear water, watching the gentle activities of the early animals on the seafloor below, when something catches your attention in a quiet corner of the microbial garden. At first, it appears to be just another small disturbance in the bacterial mat, the kind of subtle movement you've grown accustomed to observing. But as you focus your attention on this particular spot, you realize that something entirely new is happening. The disturbance is different from the smooth, gliding trails of the disc-shaped creatures or the gentle burrowing activities of the segmented worms. This movement has a more purposeful quality, a sense of structure and organization that immediately sets it apart from anything you've seen before. The bacterial mat doesn't just ripple and flow around this new presence. It seems to be actively disturbed by something with substance, something with weight and form. As you drift closer, descending through the warm water layers toward the seafloor, the source of this disturbance gradually comes into view. What emerges from beneath the microbial carpet is unlike any creature you've encountered in these ancient seas. It's larger than the other animals, for one thing, though still quite small by modern standards, perhaps the size of a silver dollar. But more importantly, it has a distinctly different architecture, a body plan that speaks of innovations that are brand new to the world of complex life. The creature that slowly reveals itself is the first trilobite, though it bears little resemblance to the elaborate forms that this group will eventually produce. This earliest representative is simple but elegant, with a body that's divided into 3 distinct lobes running from front to back. Hence the name trilobite, which means 3-lobed. The central lobe runs down the middle of its back like a spine, while 2 side lobes curve gracefully around the edges of its body, creating a form that's both symmetrical and purposeful. What's most remarkable about this first trilobite is not just its size or its segmented body plan, but the fact that it possesses something that no complex animal has ever had before, a hard shell. As it moves across the seafloor, you can see that its entire back is covered with a tough, calcified exoskeleton that protects its soft internal organs, while still allowing for flexible movement. This shell has a translucent quality in the filtered underwater light, like polished amber or mother of pearl, and it gleams softly as the creature moves. The development of this hard exoskeleton represents one of the most significant innovations in the history of life. For the first time, an animal has found a way to armor itself against the challenges of existence while maintaining the ability to move and grow and adapt. The shell is not a simple, uniform covering, but a complex structure made up of many individual segments, each one carefully shaped to allow for maximum protection and flexibility. As this first trilobite moves across the bacterial mat, you can observe the intricate mechanics of its locomotion. Unlike the flowing, undulating movements of the earlier soft-bodied creatures, the trilobite walks with a series of coordinated leg movements that are hidden beneath its protective shell. You can't see the legs themselves, but you can observe their effects. The steady, rhythmic progression across the seafloor that speaks of a sophisticated system of appendages working in perfect coordination. The trilobites' method of feeding is equally revolutionary. Instead of simply absorbing nutrients from the bacterial mat like many of the earlier creatures, it appears to be actively processing the sediment, somehow extracting food particles with efficiency that suggests the presence of specialized feeding structures. As it moves, it leaves behind a trail that's noticeably different from those created by other animals. More disturbed, more thoroughly processed, indicating that this creature is interacting with its environment in entirely new ways. The water around this first trilobite seems to shimmer with a different quality, as if the presence of this armored creature has somehow changed the very nature of the underwater environment. The gentle currents that flow across the seafloor interact with its hard shell in ways that create tiny eddies and vortices, patterns of water movement that are more complex and dynamic than anything produced by the soft-bodied animals. But perhaps most remarkable of all is what happens when you manage to position yourself to view the trilobite from the front. They're set into the forward part of its shell are two dark spots that can only be described as eyes. These are not the simple, light-sensitive cells that some of the earlier creatures possessed, but actual compound eyes, complex optical organs capable of forming images and detecting movement with a precision that represents a quantum leap in sensory capability. The eyes of this first trilobite are relatively simple compared to what the group will eventually develop, but they're still marvels of biological engineering. Each eye is composed of hundreds of individual lenses, each one perfectly shaped to focus light on a specialized nerve cells beneath. The entire structure is protected by a clear, calcified covering that allows light to pass through while preventing damage to the delicate optical components within. With these eyes, the trilobite can see its world in ways that no animal has ever seen before. It can detect the movements of other creatures from a distance, identify areas of the seafloor that offer the best feeding opportunities, and navigate through its underwater environment with a precision that gives it enormous advantages over its blind or nearly blind neighbors. This innovation alone would be enough to revolutionize life in the Cambrian seas, but it's just one of many features that make the trilobites such remarkable creatures. As you watch this first trilobite exploring its domain, you begin to notice that it's not alone. In other areas of the seafloor, other disturbances in the bacterial mats signal the presence of additional trilobites. They don't all look exactly the same. Even in these early stages, the group is beginning to experiment with different body sizes, different shell shapes, and different approaches to making a living on the ancient seafloor. Some of the trilobites are smaller and more delicate, with shells that seem almost transparent in the filtered sunlight. These appear to specialize in feeding on the finest particles in the bacterial mats, their movements quick and precise as they select only the most nutritious morsels. Others are larger and more robust, with thicker shells and more powerful appendages that allow them to burrow more deeply into the sediment and access food sources that are beyond the reach of other creatures. The diversity that's beginning to appear among the trilobites is remarkable, especially considering that the entire group has only recently evolved. It's as if they've discovered a successful body plan and are now exploring all the different ways that plan can be modified and specialized for different ecological niches. Each variation represents an experiment in adaptation, a test of how the basic trilobite design can be optimized for specific conditions and opportunities. The interaction between these early trilobites and the other creatures on the seafloor is fascinating to observe. The trilobites don't seem to be aggressive predators, at least not in any sense that would be familiar to modern observers. Instead, they appear to coexist peacefully with the soft-bodied animals, each group occupying its own particular niche in the seafloor ecosystem. The trilobites' superior vision and mobility give them access to resources that the other creatures can't exploit, but they don't seem to use these advantages to dominate or displace their neighbors. If anything, the presence of the trilobites seems to make the entire seafloor community more dynamic and diverse. Their movements create new patterns of water circulation that benefit the bacterial mats, while their feeding activities help distribute nutrients and particles to areas where other creatures can take advantage of them. Their hard shells, when they're eventually shed during molting, provide new types of habitat and shelter for smaller organisms. The molting process itself is something entirely new in the history of complex life. As trilobites grow, their rigid exoskeletons eventually become too small to accommodate their expanding bodies. When this happens, they must shed their old shells and grow new, larger ones, a process that requires the creature to become temporarily vulnerable while its new exoskeleton hardens. The discarded shells don't simply disappear. They become part of the seafloor environment, creating small shelters and hiding places that other creatures can use. The chemistry of the water begins to change subtly as more and more trilobites appear on the seafloor. The calcium carbonate that they extract from the seawater to build their shells represents a new pathway for mineral cycling in the marine environment. For the first time, large quantities of dissolved minerals are being converted into solid structures by animal activity, a process that will eventually have profound effects on the chemistry of the world's oceans. The optical properties of the water also begin to change as the trilobites become more numerous. Their hard, reflective shells scatter and redirect light in ways that create new patterns of illumination on the seafloor. Areas that were once uniformly lit by the filtered sunlight from above now show complex patterns of brightness and shadow that shift and change as the trilobites move through their underwater landscape. Temperature gradients in the water become more complex as well. The trilobites' metabolic activity generates heat, but their shells also serve as thermal masses that absorb and release heat energy in response to temperature changes in the surrounding water. This creates microenvironments around each trilobite that have slightly different thermal characteristics from the background water temperature. The sensory world that the trilobites inhabit is richer and more complex than anything that has existed before in the Earth's oceans. Their compound eyes can detect not only the shape and movement of objects, but also subtle differences in light intensity and possibly even color. Some species seem to be able to detect polarized light, which would give them additional information about the underwater light environment and possibly help them navigate through their three-dimensional world. Sound, too, begins to play a role in the trilobite environment. While these ancient seas are still far quieter than modern oceans, the movements of the trilobites and their interactions with the seafloor create subtle acoustic signals that can travel through the water. Some trilobites may be able to detect these sounds, giving them additional sensory information about their surroundings and the activities of their neighbors. The behavioral complexity that the trilobites display is remarkable for such early animals. They show clear evidence of being able to learn from experience, modifying their feeding and movement patterns based on the success or failure of previous activities. They can navigate across the seafloor with apparent purpose, suggesting some form of spatial memory that allows them to remember the locations of favorable feeding areas or suitable shelter. Social behaviors are also beginning to emerge among some trilobite species. While they're not forming the complex social structures that will characterize some later animals, there's evidence that trilobites can recognize and respond to the presence of other members of their own species. Sometimes they seem to coordinate their feeding activities, working together to process large areas of bacterial mat more efficiently than any individual could manage alone. The reproductive behaviors of these early trilobites are still largely mysterious, but there are occasional glimpses of activities that suggest sophisticated mating rituals and parental care strategies. Some species seem to gather in groups during certain periods, possibly for spawning, while others show evidence of protecting their eggs or young by creating special burrows or shelters. As the number of trilobites on the seafloor continues to increase, their collective impact on the environment becomes more and more apparent. The bacterial mats show signs of adaptation to the increased grazing pressure, developing new growth strategies and possibly new chemical defenses. The sediment structure becomes more complex as trilobite burrowing activities create networks of tunnels and chambers that extend deep into the seafloor. The water column itself shows increased biological activity as trilobite waste products and shed exoskeletons provide new nutrients for planktonic organisms. The entire ecosystem is becoming more interconnected and interdependent, with energy and materials cycling through the system in increasingly complex patterns. Yet despite all this activity and innovation, the overall character of these ancient seas remains peaceful and nurturing. The trilobites pursue their various activities with the same unhurried patience that characterizes all life in this underwater world. They feed and grow and reproduce at rates that are measured in seasons rather than hours, following biological rhythms that are perfectly synchronized with the slow cycles of the ancient Earth. The light that filters down through the crystal-clear water continues to bathe everything in a golden, dreamlike glow that makes even the most mundane activities seem touched with magic. The trilobites move through this underwater landscape like living jewels, their translucent shells catching and refracting the light in patterns that create tiny rainbows in the water around them. As you float here in this ancient sea, watching the birth and early diversification of one of the most successful groups of animals that has ever lived, you can feel the profound significance of what you're witnessing. These creatures represent a fundamental breakthrough in the complexity and sophistication of life on Earth. They are the first animals to combine mobility, sensory capability, and protective armor in a single, integrated package that gives them unprecedented control over their environment and their destiny. The trilobites are no longer just another component of the seafloor ecosystem. They're beginning to reshape that ecosystem in their own image, creating new opportunities for themselves and for the countless other creatures that share their underwater world. The age of simple, soft-bodied animals is coming to an end, and the age of complex, sophisticated marine life is about to begin in earnest. And this is still just the beginning of their story. The trilobites you're observing now are the primitive ancestors of forms that will eventually become so elaborate and specialized that they'll seem almost alien to modern eyes. They will develop compound eyes with thousands of lenses, bodies with dozens of segments, and appendages specialized for functions that haven't even been invented yet. They will colonize every type of marine environment, from the shallowest tide pools to the deepest ocean trenches, becoming the dominant life form in the Earth's seas for longer than any other group of complex animals. But for now, in these peaceful Cambrian waters, they're still learning how to be trilobites, still discovering the possibilities inherent in their revolutionary new body plan. Each individual is an experiment in adaptation, each species a test of how the trilobite design can be optimized for different challenges and opportunities. The warm water that surrounds you pulses with potential, carrying within it the seeds of forms and behaviors that will not fully flower for millions of years to come. As the days drift by in these ancient seas, measured not in hours, but in the slow cycles of tides and seasons, you begin to witness the transformation of the trilobites from curious newcomers to undisputed masters of their underwater domain. The change is gradual but profound, unfolding with the patient rhythm that characterizes all evolution in this primordial world. What begins as a handful of experimental creatures becomes a thriving community, and then something approaching a civilization of arthropods that reshapes the very nature of life on the seafloor. The morning light filtering down through the crystal-clear water reveals a seafloor that looks markedly different from the one you first encountered. Where once there were simple bacterial mats broken only by the gentle trails of soft-bodied creatures, now there's a complex landscape of activity and purpose. The trilobites have established territories and pathways, feeding grounds and resting areas, creating the first organized communities in the history of complex animal life. As you drift closer to the bottom, following a gentle thermal current that carries you downward through the perfectly warm water, you can observe the intricate details of how these remarkable creatures have adapted to their environment. The basic trilobite body plan has proven to be incredibly versatile, and different species have already begun to modify it in fascinating ways to exploit different opportunities on the ancient seafloor. Some trilobites have evolved to become expert burrowers, their shells streamlined and their digging appendages strengthened to allow them to tunnel deep into the sediment beneath the bacterial mats. These subterranean specialists create extensive networks of tunnels and chambers that honeycomb the seafloor, providing them with protection from predators and access to food sources that surface-dwelling creatures cannot reach. Their burrows also serve as shelter for other small animals, creating the first examples of engineered habitat modification in Earth's history. Other trilobites have specialized for life on the surface, developing broader, flatter shells that distribute their weight evenly across the soft bacterial mats. These surface gliders move with elegant efficiency across the seafloor, their wide shells acting like snowshoes that prevent them from sinking into the soft sediment. Their feeding appendages have become remarkably delicate and precise, allowing them to harvest the bacterial mats with surgical precision while leaving the underlying growth structures intact. Still, other trilobites have begun to explore the water column itself, developing swimming abilities that allow them to rise up from the seafloor and cruise through the open water like living submarines. These pelagic pioneers have lighter, more streamlined shells and modified appendages that can function as both swimming paddles and filtering devices for capturing planktonic food. They represent the first steps toward the colonization of the open ocean, expanding the trilobite empire beyond the confines of the seafloor. The diversity of feeding strategies that the trilobites have developed is particularly remarkable to observe. Some species have evolved to become filter feeders, using specialized appendages to strain microscopic organisms and organic particles from the water column. They position themselves in areas where currents are strongest, creating living nets that capture nutrients as they flow past. Their rhythmic feeding motions create gentle whirlpools and eddies that enhance water circulation and bring even more food within their reach. Other trilobites have become deposit feeders, specializing in processing the nutrient-rich sediments that accumulate in quiet areas of the seafloor. They move across these areas like living vacuum cleaners, ingesting vast quantities of sediment and extracting every bit of organic matter before excreting the clean sand and silt behind them. Their feeding trails create distinctive patterns on the seafloor that persist for days or weeks, marking the pathways of their systematic harvesting activities. Perhaps most fascinating are the trilobites that have begun to show signs of active predation. Though their approach to hunting is far more gentle and patient than anything that would be familiar to modern observers. These predatory species have developed more robust shells and stronger appendages that allow them to capture and process other small animals. But rather than engaging in violent struggles, they seem to specialize in overwhelming their prey through persistence and superior mobility, gradually wearing down their victims' defenses until they can be safely consumed. The sensory capabilities of the trilobites continue to evolve and improve as well. Their compound eyes become larger and more sophisticated, with some species developing visual systems that rival those of modern arthropods in their complexity and acuity. These advanced eyes allow them to detect movement and changes in light intensity with remarkable precision, giving them significant advantages in both finding food and avoiding danger. Some trilobite species have begun to develop additional sensory structures as well. Specialized appendages that can detect chemical signals in the water allow them to track food sources or locate mates from considerable distances. Other species show evidence of mechanoreceptors that can detect vibrations and water movements, giving them awareness of activities happening far beyond the range of their vision. The social behaviors of the trilobites become increasingly complex as their numbers grow and their interactions become more frequent. While they're still far from developing the elaborate social structures that characterize some modern arthropods, there's clear evidence of communication and cooperation among individuals of the same species. Some trilobites engage in what appears to be chemical communication, releasing specific substances into the water that trigger behavioral responses in nearby individuals. Mating behaviors among the trilobites are beginning to show remarkable sophistication as well. During certain seasons, when water temperature and chemical conditions are optimal, trilobites of the same species gather in large groups for spawning events. These gatherings are peaceful affairs, with individuals positioning themselves in carefully organized patterns that maximize the chances of successful fertilization while minimizing competition and conflict. The reproductive strategies themselves show considerable diversity among different trilobite species. Some appear to be broadcast spawners, releasing their eggs and sperm into the water column where fertilization occurs randomly. Others show evidence of more directed mating, with males and females engaging in elaborate courtship rituals before releasing their reproductive cells in synchronized timing that ensures maximum fertilization success. Parental care behaviors are also beginning to emerge among some trilobite species. Certain females appear to guard their eggs after laying them, using their bodies to protect the developing embryos from potential threats. Some species create special brooding chambers within their burrows where eggs can develop in safety, while others carry their eggs attached to specialized appendages until they're ready to hatch. The growth and development patterns of trilobites reveal another layer of their remarkable adaptation to life in these ancient seas. Like all arthropods, trilobites must molt their exoskeletons periodically as they grow, but they've evolved this process into something approaching an art form. The timing of molting is carefully coordinated with food availability and environmental conditions, ensuring that each individual is in optimal condition when they become temporarily vulnerable during the shell-changing process. The molting process itself is a marvel of biological engineering. The trilobite begins by secreting enzymes that weaken the connections between the old exoskeleton and the underlying tissue. Then, by absorbing water and inflating its body, it creates hydraulic pressure that splits the old shell along predetermined fracture lines. The creature then carefully extracts itself from its outgrown armor, emerging with a new, soft exoskeleton that gradually hardens over the course of several hours or days. During the brief period when their exoskeletons are soft, trilobites become remarkably vulnerable, and they've evolved elaborate strategies for protecting themselves during this critical time. Some species retreat deep into their burrows and seal the entrances until their new shells harden. Others gather in groups where individuals can take turns molting while their hard-shelled neighbors provide protection. Still others time their molting to coincide with periods of low predator activity or optimal environmental conditions. The shed exoskeletons don't simply disappear from the environment. They become important components of the seafloor ecosystem in their own right. Some are quickly broken down by bacteria and other decomposers, releasing nutrients back into the water column. Others are colonized by small organisms that use them as temporary homes or feeding platforms. The most durable shells become permanent parts of the seafloor architecture, creating small shelters and landmarks that persist for months or even years. The impact of all this trilobite activity on the broader seafloor ecosystem is profound and far-reaching. The bacterial mats that once dominated the bottom show clear signs of adaptation to the increased grazing pressure and physical disturbance created by trilobite feeding and movement. Some bacterial communities have developed more robust growth forms that can withstand the constant harvesting, while others have evolved chemical defenses that make them less palatable to trilobite feeders. The physical structure of the seafloor itself has been transformed by trilobite engineering activities. The extensive burrow systems created by fossorial species have fundamentally altered the way water and nutrients move through the sediment. These underground networks create channels for fluid flow that increase the exchange of materials between the sediment and the overlying water, enhancing the productivity of the entire seafloor ecosystem. The water column above the seafloor shows increased biological activity as well, stimulated by the nutrients and particles released by trilobite feeding and waste production. Planktonic organisms become more abundant and diverse, providing food for the filter-feeding trilobites and creating the first examples of complex food webs in the Earth's oceans. Temperature and chemical gradients in the water become more complex as trilobite metabolism and behavior create localized variations in the marine environment. Areas of high trilobite activity tend to be slightly warmer and richer in dissolved nutrients, while areas where few trilobites are present remain closer to the background conditions of the ancient sea. The optical properties of the underwater environment change as well, as the movements of thousands of trilobites stir up sediment particles and create complex patterns of light and shadow on the seafloor. The reflective properties of their shells add new dimensions to the underwater light field, creating sparkles and glints that dance through the water as the creatures move. Sound becomes a more prominent feature of the trilobite environment as well. While these ancient seas are still much quieter than modern oceans, the movements of trilobites across the seafloor and their interactions with each other create subtle acoustic signals that travel through the water. Some species may have evolved the ability to detect and interpret these sounds, adding an auditory dimension to their sensory world. The seasonal rhythms of trilobite life become more pronounced as their populations grow and their behaviors become more synchronized. During certain times of the year, when food is abundant and conditions are optimal, trilobite activity reaches peak levels. The seafloor buzzes with feeding, mating, molting, and social interactions that create an underwater metropolis of arthropod activity. During other seasons, when food becomes scarcer or environmental conditions become less favorable, trilobite activity decreases markedly. Some species enter states of reduced metabolism that allow them to survive on minimal food intake, while others migrate to more favorable areas of the seafloor. These seasonal migrations create moving populations that can be observed traveling across the underwater landscape in organized groups. The navigational abilities required for these migrations suggest that trilobites have developed sophisticated orientation mechanisms. Some species appear to use the angle and intensity of sunlight filtering down through the water as a compass, while others may navigate using chemical gradients or magnetic fields. The precision with which they can return to specific feeding or breeding areas suggests spatial memory capabilities that are remarkably advanced for such early animals. Territorial behaviors are beginning to emerge among some trilobite species as well. Certain individuals or groups establish and defend specific areas of the seafloor that offer particularly good feeding or shelter opportunities. These territories are maintained through a combination of chemical marking, physical presence, and occasional confrontations with intruders, though the conflicts are typically resolved through displays of strength rather than actual combat. The establishment of these territories creates a more organized and predictable structure to trilobite communities. Regular pathways develop between feeding areas and shelters, creating the first transportation networks in the history of animal life. These pathways become worn channels in the seafloor that guide water flow and concentrate nutrients, making them attractive to other organisms as well. Interspecies interactions among different types of trilobites show remarkable sophistication and diversity. Some species appear to have developed commensalistic relationships, where one species benefits from the activities of another without causing harm. For example, small trilobites often follow larger burrowing species, taking advantage of the disturbed sediment and exposed food particles created by the bigger animals' digging activities. Other trilobite species show what appears to be the beginning of competitive exclusion, where closely related species with similar ecological requirements partition the available resources in ways that minimize direct competition. This might involve feeding at different times of day, specializing on different food sources, or occupying different physical zones of the seafloor environment. The complexity of these ecological relationships represents a fundamental shift in the nature of life on Earth. For the first time, animal communities are showing the kind of intricate interdependencies and specialized roles that characterize modern ecosystems. The trilobites are not just living in their environment. They're actively creating and modifying that environment in ways that benefit themselves and influence countless other organisms. As you observe all this activity from your floating vantage point in the warm, clear water, you begin to understand that you're witnessing something truly revolutionary in the history of life on Earth. The trilobites have not simply added another component to the existing seafloor ecosystem. They have fundamentally transformed what it means to be an animal living on the ocean floor. Their combination of mobility, sensory capability, and protective armor has given them unprecedented control over their environment and their interactions with other organisms. They are the first animals to actively engineer their habitat, the first to develop complex social behaviors, and the first to establish the kind of ecological relationships that will eventually give rise to the intricate food webs and ecosystem dynamics that characterize modern marine environments. The warm water that surrounds you continues to pulse with the activities of these remarkable creatures, carrying chemical signals and waste products, nutrients and reproductive cells, the sounds of movement and the vibrations of countless tiny feet walking across the ancient seafloor. This is no longer just a sea dotted with primitive life forms. This is becoming a complex, integrated ecosystem where every component influences every other component in an intricate dance of biological interaction. And still, this is only the beginning of the trilobite story. The species you're observing now are the pioneers, the early experimenters who are still discovering the possibilities inherent in their revolutionary body plan. In the millions of years to come, their descendants will develop forms and capabilities that will push the boundaries of what's possible for arthropod life, creating some of the most elaborate and beautiful creatures that have ever lived in Earth's oceans. As you continue floating in these ancient waters, the passage of time becomes marked not by days or seasons, but by the gradual flowering of one of the most spectacular examples of evolutionary diversification in Earth's history. Millions of years drift by like gentle currents, each bringing subtle but profound changes to the trilobite communities that have made these seafloors their home. What began as a single, simple body plan has now blossomed into a bewildering array of forms, each one perfectly adapted to its own particular niche in the ever-expanding underwater ecosystem. The warm water that surrounds you carries with it the chemical signatures of this great diversification. Dissolved minerals flow in complex patterns as different trilobite species modify their shells with new compounds and structures. Calcium carbonate, phosphate, and silica are incorporated into exoskeletons in innovative ways, creating shells that range from gossamer thin and translucent to massively thick and nearly opaque. The very chemistry of the ocean is being rewritten by these industrious arthropods as they experiment with new ways to build their protective armor. Drifting closer to the seafloor, you encounter your first glimpse of how dramatically the trilobite world has transformed. Where once there were just a few basic forms crawling across the bacterial mats, now there's a veritable parade of shapes and sizes that would challenge the imagination of any artist. Some trilobites have become so specialized that they barely resemble their common ancestors, their bodies stretched and modified to exploit ecological opportunities that didn't even exist when the group first evolved. In the shallow areas of the seafloor, where the sunlight penetrates most strongly through the crystal-clear water, you encounter the giants of the trilobite world. These magnificent creatures have grown to sizes that would seem impossible for arthropods, with some individuals stretching nearly 2 feet in length. Their massive shells gleam like polished bronze in the filtered sunlight, segmented into dozens of individual plates that flex and move with fluid grace as these behemoths glide across the sea bottom. These giant trilobites move with surprising elegance despite their size, their numerous legs working in perfect coordination to carry their substantial bodies across the seafloor without disturbing the delicate bacterial communities beneath them. Their feeding apparatus has evolved to match their scale, with massive filtering systems that can process enormous volumes of water and sediment, extracting nutrients with industrial efficiency while maintaining the gentle, non-destructive approach that characterizes all trilobite feeding. The eyes of these giants represent some of the most sophisticated optical systems that have ever evolved. Each compound eye contains thousands of individual lenses, arranged in complex geometric patterns that provide nearly complete spherical vision. Some species have developed eyes so large that they dominate the entire front portion of their shells, creating creatures that seem to be more eye than body. The visual acuity these organs provide allows the giants to detect movement and changes in their environment from remarkable distances, making them the ultimate sentinels of the ancient seafloor. But not all evolutionary experimentation has led toward gigantism. In the deeper, darker regions of the seafloor, where the sunlight barely penetrates, you discover trilobites that have gone in exactly the opposite direction. These miniature species, some no larger than your fingernail, represent the other extreme of size adaptation. Their tiny bodies are perfectly suited for life in the interstitial spaces between sand grains and bacterial colonies, exploiting a microscopic world that larger animals cannot access. These diminutive trilobites have evolved their own remarkable specializations. Their shells are often highly flexible, allowing them to squeeze through spaces that would seem impossibly small for an armored creature. Their appendages have become incredibly delicate and precise, capable of manipulating individual bacterial cells and organic particles with surgical accuracy. Some species have developed bioluminescent organs that allow them to create their own light in the perpetual twilight of their deep-sea environment. Between these extremes of giant and dwarf, the trilobite world has exploded into a middle realm of forms that showcase every conceivable variation on the basic arthropod body plan. Some species have developed elongated, snake-like bodies with dozens of segments, allowing them to undulate through the water column like living ribbons. Others have become broad and flat, their shells expanded into wing-like structures that allow them to glide through the water with minimal effort. The feeding specializations that have evolved are particularly remarkable to observe. Some trilobites have developed incredibly long, thin appendages that they use like fishing lines to capture small organisms from the water column. These appendages can extend far beyond the boundaries of their shells, reaching into crevices and spaces that the trilobites themselves cannot access. The precision with which they manipulate these tools suggests a level of sensory control that rivals the most sophisticated modern arthropods. Other species have evolved shells with complex internal chambers that function as sophisticated filtering systems. Water enters through specialized openings and flows through elaborate internal passages where nutrients are extracted and waste products are processed before the cleaned water is expelled. These living filtration plants can process vast volumes of seawater, concentrating and consuming microscopic organisms with remarkable efficiency. Perhaps most fascinating are the trilobites that have begun to develop symbiotic relationships with other organisms. Some species have shells that are riddled with small chambers and cavities that provide homes for bacteria, algae, and other microscopic life forms. These partnerships benefit both organisms. The trilobites gain access to nutrients produced by their symbionts, while the smaller organisms receive protection and a stable environment in which to live and reproduce. The visual systems of trilobites have diversified just as dramatically as their body forms. While the basic compound eye design remains consistent across most species, the variations in size, shape, and complexity are astounding. Some trilobites have developed eyes that wrap around nearly their entire heads, providing complete panoramic vision that allows them to monitor their environment in all directions simultaneously. Other species have evolved highly specialized eyes adapted for specific environmental conditions. Deep-water trilobites often have enlarged eyes with enhanced light-gathering capabilities that allow them to function in the dim conditions of the seafloor depths. Some have developed eyes that are sensitive to polarized light, giving them additional information about the underwater light environment and possibly helping them navigate through their three-dimensional world. A few remarkable species have even begun to experiment with multiple eye types on the same individual. These trilobites have their normal compound eyes for general vision, plus additional specialized eyes that are optimized for detecting movement, changes in light intensity, or even infrared radiation. This multimodal visual system gives them an incredibly rich and detailed picture of their environment that far exceeds the capabilities of their simpler ancestors. The locomotory adaptations of trilobites have become equally diverse and sophisticated. While the basic walking pattern remains similar across most species, The appendages themselves have been modified in countless ways to suit different lifestyles and environments. Some trilobites have developed powerful digging claws that allow them to excavate complex burrow systems in the seafloor sediment. Others have evolved paddle-like appendages that make them efficient swimmers, capable of rising up from the bottom and cruising through the open water column. A few species have developed appendages that can function in multiple modes, switching between walking, swimming, and digging depending on the situation. These multi-purpose limbs represent remarkable examples of biological engineering, with joints and muscles that can reconfigure themselves to optimize performance for whatever task is at hand. The reproductive strategies of trilobites have also diversified in fascinating ways. While many species still practice the basic broadcast spawning that characterized their ancestors, others have evolved elaborate courtship rituals and mating systems. Some males have developed enlarged appendages or shell ornamentations that they use in competitive displays to attract females. Others have evolved chemical communication systems that allow them to coordinate their reproductive activities across large areas of the seafloor. Parental care behaviors have become increasingly sophisticated among many trilobite species. Some females construct elaborate brooding chambers where their eggs can develop in safety, while others carry their young attached to specialized appendages until they're large enough to fend for themselves. A few species have even developed forms of cooperative breeding, where multiple adults work together to protect and care for the young of the group. The molting process, which was already complex in early trilobites, has become even more elaborate and precisely controlled in these advanced forms. Some species have evolved the ability to molt only specific portions of their exoskeleton at a time, allowing them to grow continuously without ever becoming completely vulnerable. Others have developed group molting behaviors, where entire communities synchronize their molting cycles to provide mutual protection during the vulnerable periods. The chemical communication systems that trilobites use have become remarkably sophisticated. Different species produce specific chemical signals that can convey information about identity, reproductive status, territorial boundaries, and even emotional states. These chemical messages can travel considerable distances through the water, allowing trilobites to communicate with each other across the vast expanses of the seafloor. Some species have developed the ability to detect and interpret chemical signals from multiple sources simultaneously, giving them detailed information about the activities and intentions of all the trilobites in their vicinity. This chemical awareness allows for complex social interactions and coordinated group behaviors that would be impossible without some form of long-distance communication. The territorial behaviors of trilobites have evolved into elaborate systems of resource management and community organization. Some species establish and maintain territories that are passed down from generation to generation, creating the first examples of inherited property in the animal kingdom. These territories are marked with chemical signals and defended through complex behavioral displays that rarely escalate to actual physical confrontation. Other species have developed communal territorial systems where groups of individuals collectively defend large areas of the seafloor. These territories are organized into zones with different functions: feeding areas, molting refuges, nursery grounds for young, and meeting places for social interactions. The complexity of these territorial arrangements rivals that of many modern animal societies. The predatory behaviors of some trilobite species have also become more sophisticated and specialized. While most trilobites remain peaceful filter feeders and deposit feeders, a few species have evolved into active hunters that pursue and capture other animals. These predatory trilobites have developed enhanced sensory systems, more powerful appendages, and behavioral strategies that allow them to successfully hunt in the competitive environment of the diverse seafloor community. However, even the predatory trilobites maintain the gentle, patient approach that characterizes all trilobite behavior. Their hunting strategies rely on stealth, persistence, and superior sensory capability rather than speed or aggression. They're more like underwater detectives than fierce predators, using their advanced eyes and chemical sensors to track their prey and then employing careful stalking techniques to get within range for capture. The impact of this great trilobite diversification on the broader marine ecosystem has been profound and far-reaching. The seafloor environment has been transformed from a relatively simple bacterial garden into a complex, multi-layered ecosystem with intricate food webs and energy flows. Different trilobite species occupy virtually every available ecological niche, from the surface of the bacterial mats to the deepest burrows in the sediment, from the water column just above the seafloor to the interstitial spaces between individual sand grains. This ecological saturation has driven the evolution of other marine organisms as well. Bacterial communities have developed new strategies for dealing with the constant grazing pressure from trilobite feeders. Some have evolved chemical defenses that make them unpalatable, while others have developed more rapid growth rates that allow them to recover quickly from harvesting. Still others have formed protective associations with certain trilobite species, gaining protection in exchange for providing nutrients. The physical structure of the seafloor has been completely reorganized by trilobite engineering activities. The simple, flat bacterial mats of earlier times have been replaced by a complex, three-dimensional landscape of burrows, mounds, feeding trails, and territorial boundaries. This structural complexity creates countless microhabitats that support an incredible diversity of smaller organisms, from bacteria and algae to primitive worms and other early animals. The water column above the seafloor has become more dynamic and productive as well. The constant activity of millions of trilobites stirs nutrients from the sediment into the overlying water, supporting larger and more diverse populations of planktonic organisms. These planktonic communities provide food for filter-feeding trilobites, creating complex feedback loops that stabilize and enhance the productivity of the entire ecosystem. Chemical cycling in the marine environment has become far more complex as different trilobite species process and concentrate various minerals and nutrients. Some species specialize in extracting particular compounds from seawater, creating localized areas of chemical depletion or concentration that influence the distribution and behavior of other organisms. This biological modification of seawater chemistry represents one of the first examples of ecosystem engineering by animal activity. The optical environment of the underwater world has been transformed as well. The movements of countless trilobites create constantly shifting patterns of light and shadow on the seafloor, while their reflective shells add sparkles and glints to the underwater landscape. Some species have evolved shells with specific optical properties that help them blend into their surroundings or communicate with other members of their species through visual signals. Sound has become a more prominent feature of the trilobite environment as the diversity and abundance of species has increased. Different species produce different acoustic signatures as they move across the seafloor, and some have evolved the ability to detect and interpret these sounds. The result is an underwater soundscape that's far richer and more complex than the nearly silent seas of earlier periods. Temperature regulation in the marine environment has become more sophisticated as well. Large concentrations of trilobites can create localized warm spots through their collective metabolic activity, while their burrowing and water circulation activities help distribute heat more evenly throughout the seafloor environment. Some species appear to actively seek out or create optimal temperature conditions for their activities. As you float here in these ancient waters, surrounded by the incredible diversity of trilobite life, you begin to understand that you're witnessing one of the most successful evolutionary radiations in Earth's history. The trilobites have not just adapted to fill available ecological niches. They have created entirely new niches and entirely new ways of being an animal in the marine environment. Their success represents the triumph of the arthropod body plan, with its combination of segmentation, jointed appendages, and external skeleton proving to be incredibly versatile and adaptable. Every conceivable variation on this basic theme has been explored, from the tiniest specialists living between sand grains to the massive giants that dominate the open seafloor, from peaceful filter feeders to active predators, from solitary wanderers to highly social community builders. The warm water that surrounds you carries within it the chemical signatures of this incredible diversity. The waste products and reproductive cells, the communication chemicals and defensive compounds, the dissolved minerals and organic nutrients that flow between the countless different species that now call these ancient seas their home. This is no longer just an ocean. It's a living, breathing ecosystem of unprecedented complexity and beauty. And yet, even as you marvel at the incredible diversity that the trilobites have achieved, you sense that their story is far from over. The forms you're observing now represent just a snapshot in time, a moment in an evolutionary journey that will continue for hundreds of millions of years. The trilobites will continue to innovate and adapt, developing even more remarkable forms and behaviors as they respond to changing environmental conditions and new evolutionary pressures. The peaceful rhythm of life in these ancient seas continues unabated, with each species following its own particular schedule of feeding, mating, molting, and social interaction. But beneath this surface tranquility, the great engine of evolution continues to work, testing new possibilities and refining successful adaptations in an endless quest for better ways to thrive in the underwater world that the trilobites have made their own. As you drift deeper into the timeless rhythm of these primordial seas, you begin to notice something remarkable about the way life unfolds in the trilobite world. Unlike the modern ocean with its sharp seasonal contrasts and dramatic weather patterns, these ancient waters follow gentler, more predictable cycles that seem to breathe with the very pulse of the planet itself. The seasons here are not marked by harsh transitions or sudden changes, but by subtle shifts in temperature, light, and chemistry that flow like slow tides across the underwater landscape. The first signs of seasonal change appear in the quality of light that filters down through the crystal clear water. During what might be called the bright season, the sun's rays penetrate deeper into the sea, illuminating the seafloor with a golden radiance that seems to energize every living thing. The water itself takes on a slightly different character during these periods, becoming even more transparent and carrying within it subtle chemical signals that trigger behavioral changes throughout the trilobite community. As the bright season begins, you can observe a gentle stirring of activity across the seafloor that's like watching an enormous underwater garden come to life. Trilobites that have been resting quietly in their burrows or moving slowly across the bacterial mats suddenly become more active and purposeful in their movements. Their feeding activities intensify, their social interactions become more frequent, and the entire seafloor takes on an atmosphere of quiet anticipation. The bacterial communities respond to the increased light as well, their photosynthetic activity ramping up to take advantage of the enhanced solar energy. The microbial mats become more colorful and robust during the bright season, their surfaces rippling with waves of green and purple and gold as different bacterial species compete for optimal positioning in the light field. This enhanced bacterial productivity provides more food for the trilobites, creating a cascade of abundance that flows throughout the entire ecosystem. Temperature changes during the bright season are subtle but significant. The water becomes perhaps a degree or two warmer, just enough to increase metabolic rates and stimulate growth without creating any stress or discomfort for the sea's inhabitants. This gentle warming penetrates deep into the seafloor sediments, activating bacterial communities that have been dormant in the cooler periods and creating new sources of nutrients for burrowing trilobites. The chemistry of the seawater itself undergoes delicate modifications during the bright season. Dissolved oxygen levels increase slightly as enhanced photosynthetic activity by bacteria and primitive algae releases more of this vital gas into the water. Trace nutrients become more abundant as increased biological activity cycles materials more rapidly through the ecosystem. These chemical changes are so subtle that they would be barely detectable to modern instruments, but they create profound effects on the behavior and physiology of the trilobites. During these bright periods, you can observe some of the most spectacular displays of trilobite behavior. Mating aggregations become more common and more elaborate, with hundreds or even thousands of individuals gathering in specific areas of the seafloor for synchronized reproductive activities. These gatherings have an almost ceremonial quality, with trilobites arranging themselves in complex geometric patterns that seem to follow rules and traditions that have been refined over millions of years. The courtship behaviors that unfold during these aggregations are mesmerizing to watch. Males of many species perform intricate dances, using their appendages to create graceful gestures and their shells to reflect light in specific patterns. Some species engage in synchronized swimming displays, with groups of individuals moving through the water column in formations that create living kaleidoscopes of color and motion. Chemical communication reaches peak intensity during the bright season as well. The water becomes rich with pheromones and other signaling molecules as trilobites communicate their reproductive status, territorial boundaries, and social intentions. These chemical messages create invisible highways of information that crisscross the seafloor, allowing trilobites to coordinate their activities across vast distances. Feeding behaviors also become more sophisticated and communal during the bright season. Some species that normally feed individually begin to work together in organized groups, systematically harvesting large areas of bacterial mat with remarkable efficiency. These cooperative feeding activities have an almost agricultural quality, with different individuals taking on specialized roles in the harvesting and processing of food resources. The molting cycles of many trilobite species are synchronized with the bright season as well. The optimal conditions of increased food availability and enhanced metabolic activity make this the ideal time for the energy-intensive process of growing new exoskeletons. You can observe trilobites in various stages of the molting process, from the initial softening of their old shells to the final hardening of their new armor. The molting process creates its own seasonal rhythms within the trilobite community. Areas of the seafloor become temporarily dominated by soft-bodied individuals who are vulnerable and require protection from their harder-shelled neighbors. These molting grounds develop their own social dynamics, with complex hierarchies and protection systems that ensure the safety of molting individuals. As the bright season gradually transitions into what might be called the quiet season, the changes are subtle but unmistakable. The light begins to penetrate less deeply into the water, taking on a softer, more diffuse quality that creates a perpetual twilight atmosphere on seafloor. The temperature drops just slightly, enough to slow metabolic processes without causing any distress to the sea's inhabitants. The bacterial communities respond to these changing conditions by shifting their growth patterns and metabolic strategies. Some species become less active, while others that are adapted to lower light conditions begin to flourish. The overall productivity of the microbial mats decreases, but the diversity of bacterial species often increases as specialized forms take advantage of the changed conditions. Trilobite behaviors shift accordingly as the quiet season progresses. The frantic activity of the bright season gives way to a more contemplative pace of life. Feeding becomes more selective and efficient, with trilobites concentrating on the highest quality food sources while expending less energy on movement and social interactions. Many species retreat deeper into their burrows or seek out protected areas where they can wait out the less favorable conditions. The quiet season is not a time of dormancy or inactivity, but rather a period of consolidation and reflection. Trilobites use this time to repair and strengthen their shells, to digest and process the nutrients they accumulated during the bright season, and to engage in the more subtle aspects of social behavior that require patience and careful observation. Some of the most sophisticated trilobite behaviors can only be observed during the quiet season. Complex territorial negotiations take place as different species adjust their boundaries and resource allocations for the changed conditions. Elaborate grooming and maintenance rituals become more common as trilobites have more time to devote to the care and maintenance of their exoskeletons and appendages. The quiet season is also when many trilobite species engage in their most advanced learning behaviors. Young individuals spend time with experienced adults, apparently acquiring the complex knowledge and skills needed to survive and prosper in their underwater world. These educational interactions have an almost scholarly quality, with patient teachers demonstrating feeding techniques, navigation methods, and social protocols to attentive students. Between the bright and quiet seasons, There are transitional periods that have their own unique characteristics. These transitions are marked by subtle changes in water circulation patterns as temperature gradients shift and create new current systems. These gentle currents carry nutrients, reproductive cells, and chemical signals throughout the seafloor environment, creating opportunities for long-distance communication and resource sharing. The transitional periods are often when the most innovative trilobite behaviors emerge. Released from the specific demands of either bright season productivity or quiet season conservation, trilobites have the freedom to experiment with new feeding strategies, new social arrangements, and new ways of interacting with their environment. Many of the most successful evolutionary innovations appear to have originated during these transitional times. The deep seasonal rhythms of the trilobite world are synchronized with astronomical cycles that operate on much longer timescales than the simple bright and quiet seasons. Over periods of thousands or tens of thousands of years, subtle changes in the Earth's orbit and the intensity of solar radiation create longer-term cycles that influence the entire marine ecosystem. During the peak periods of these longer cycles, the trilobite world experiences golden ages of abundance and diversity. Food becomes more plentiful, conditions become more stable, and populations can grow to sizes that support even more complex social structures and behaviors. These are the times when new species evolve most rapidly and when the most elaborate forms and adaptations develop. During the minimum periods of the longer cycles, the trilobite world becomes more conservative and efficiency-focused. Resources become scarcer, conditions become more variable, and only the most well-adapted and efficient species can maintain large populations. These challenging periods serve as evolutionary filters that eliminate less successful forms and preserve only the most robust and adaptable lineages. The water temperature variations associated with these longer cycles are minimal by modern standards, but they're sufficient to drive significant changes in trilobite behavior and distribution. During cooler periods, many species migrate toward warmer areas of the seafloor or develop physiological adaptations that allow them to function more efficiently at lower temperatures. During warmer periods, species can expand their ranges and explore new habitats that were previously too cold to support large populations. The chemical cycles of the ancient oceans also follow these longer-term patterns. During some periods, the concentration of dissolved nutrients increases, supporting larger and more diverse bacterial communities that in turn support more trilobites. During other periods, nutrient levels decrease, forcing the entire ecosystem to become more efficient in its use of available resources. These chemical variations create opportunities for different types of trilobite specialists to flourish at different times. Species that are highly efficient at extracting nutrients from low-concentration solutions become dominant during nutrient-poor periods, while species that can rapidly exploit high-concentration nutrient pulses take advantage during abundant times. The geological processes that shape the seafloor also follow seasonal and cyclical patterns, though these operate on timescales that are much longer than biological seasons. Gradual changes in sea level, sediment deposition patterns, and tectonic activity create new habitats and eliminate others, driving continuous evolution and adaptation in trilobite communities. During periods of rising sea level, vast new areas of shallow seafloor become available for colonization, triggering rapid evolutionary radiations as trilobite species adapt to exploit these new opportunities. During periods of falling sea level, habitats become more restricted and competitive, leading to evolutionary pressure for increased efficiency and specialization. Volcanic activity, while rare and gentle in these ancient seas, creates its own seasonal effects. Underwater volcanic vents release nutrients and minerals that temporarily enrich local areas of the seafloor, creating oases of abundance that attract trilobites from great distances. The chemistry of these volcanic inputs can persist for months or years, creating temporary but productive ecosystems around the vent sites. The interaction between all these different seasonal and cyclical processes creates an incredibly complex temporal landscape that shapes every aspect of trilobite life. Individual trilobites, must navigate not only the immediate seasonal changes in their local environment, but also the longer-term cycles that affect resource availability, population dynamics, and evolutionary pressures. The most successful trilobite species are those that have evolved the ability to predict and prepare for these various cycles. Some species show evidence of being able to anticipate seasonal changes and adjust their behavior accordingly, storing resources during abundant periods and reducing activity during lean times. Others have evolved flexible life history strategies that allow them to take advantage of whatever conditions happen to prevail. The social structures of trilobite communities also show adaptation to seasonal and cyclical patterns. During abundant periods, social hierarchies become more elaborate and resource sharing becomes more common. During scarce periods, social structures become more egalitarian and focused on survival rather than competition. Communication systems become more sophisticated during certain seasons as well. The chemical signals that trilobites use to communicate carry farther and remain active longer in the cooler, denser water of the quiet seasons. This enhanced communication ability allows for more complex social coordination and long-distance planning during these periods. Territory sizes and boundaries also fluctuate with seasonal changes. During abundant periods, territories can be smaller because resources are more concentrated and readily available. During scarce periods, territories must be larger to encompass sufficient resources for survival, leading to complex negotiations and adjustments in territorial boundaries. The reproductive cycles of trilobites show remarkable synchronization with multiple seasonal and cyclical patterns simultaneously. Many species time their reproduction to coincide with optimal feeding conditions for their offspring, while also taking advantage of favorable environmental conditions for egg development and larval survival. Some species have evolved reproductive strategies that span multiple seasons, with different stages of reproduction and development occurring during different seasonal conditions. This temporal diversification of reproductive activities helps ensure that at least some offspring will encounter favorable conditions regardless of year-to-year variations in environmental cycles. As you float here in these ancient waters, observing the gentle ebb and flow of seasonal rhythms in the trilobite world, you begin to appreciate the incredible complexity and sophistication of life in these primordial seas. The trilobites have not simply adapted to their environment. They have learned to dance with the multiple rhythms and cycles that govern their underwater world, creating a civilization that is perfectly synchronized with the deeper patterns of planetary existence. The warm water that surrounds you carries within it the accumulated wisdom of millions of years of seasonal adaptation, the chemical memories of countless cycles of abundance and scarcity, growth and consolidation, innovation and conservation. This is a world where time itself has become a resource to be used wisely, where the ability to read and respond to temporal patterns is just as important as the ability to find food or avoid predators. The peaceful rhythm of seasonal change continues around you, as reliable and comforting as a heartbeat, marking the passage of time in the trilobite world with gentle pulses of light and warmth, abundance and quiet reflection. In this rhythm, you can sense the deep stability that has allowed these remarkable creatures to flourish for so long in their underwater paradise, adapting and evolving while maintaining the essential harmony that makes their world such a peaceful and nurturing place to exist. As you drift through these ancient waters, your attention gradually expands beyond the fascinating world of the trilobites to encompass the broader community of creatures that share their underwater realm. The trilobites, remarkable as they are, do not exist in isolation. They are part of an intricate web of life that includes some of the most extraordinary and beautiful organisms that have ever lived in Earth's oceans. These companions of the deep create a supporting cast that makes the trilobite world even more rich and complex than it would be otherwise. Floating gently above the seafloor, you begin to notice movement in the water column that's different from the steady crawling and burrowing activities of the trilobites below. These are the swimmers and drifters of the ancient seas, creatures that have adapted to life in the open water rather than on the bottom. Some move with the graceful, pulsing motions of jellyfish, their translucent bodies contracting and expanding in rhythms that propel them through the crystal-clear water with hypnotic regularity. These ancient jellyfish-like creatures are marvels of biological engineering. Their bodies so transparent that they're almost invisible except when they catch the light just right and sparkle like living crystals. Some are no larger than coins, drifting through the water like animated snowflakes, while others grow to impressive sizes with bell-shaped bodies that pulse majestically as they cruise through their three-dimensional habitat. The jellies feed by trailing long, delicate tentacles that drift behind them like underwater streamers. These tentacles are armed with microscopic stinging cells that can paralyze tiny organisms, but their effect is so gentle that prey animals simply become sleepy and relaxed rather than experiencing any distress. The paralyzed prey is then slowly drawn up to the jellyfish's mouth and consumed in a process that's more like a peaceful absorption than active predation. Watching these creatures feed is like observing an underwater ballet. The jellies move through areas of the water column where small organisms are concentrated, their tentacles sweeping gracefully through the water to collect their microscopic meals. The entire process has a dreamy, almost meditative quality that perfectly matches the peaceful atmosphere of these ancient seas. Some of the most remarkable swimmers in the trilobite world are creatures that look like living flowers or underwater plants, but which are actually sophisticated animals with complex internal structures. These sea lily-like organisms, technically called crinoids, attach themselves to the seafloor with flexible stalks that can bend and sway with the gentle currents. At the top of each stalk is a crown of feathery arms that spread out like the petals of an exotic flower. The crinoids feed by filtering small particles and organisms from the water column, using their feathery arms to create gentle currents that draw food toward their central mouths. The coordination required for this feeding process is remarkable. Each arm moves independently, but in harmony with all the others, creating complex three-dimensional patterns of water flow that maximize food capture while minimizing energy expenditure. During feeding, entire groves of crinoids wave back and forth in unison, creating underwater forests that undulate with the rhythm of the currents. The sight is mesmerizing, like watching an underwater meadow of flowers swaying in a gentle breeze. The movement is so coordinated and graceful that it seems almost choreographed, as if the crinoids are performing an elaborate dance for the pleasure of any observers. The crinoids come in a remarkable variety of forms, from simple, single-stalked individuals to complex, branching colonies that create intricate three-dimensional structures on the seafloor. Some species have developed specialized appendages that allow them to capture larger prey, while others have evolved symbiotic relationships with smaller organisms that live among their feathery arms. Among the most beautiful companions of the trilobites are the early corals, though these ancient forms bear little resemblance to their modern descendants. These primitive corals are solitary creatures, each individual living alone rather than forming the massive colonial structures that characterize modern coral reefs. They look like small, cup-shaped flowers scattered across the seafloor, their delicate skeletal structures gleaming like polished ivory in the filtered sunlight. The ancient corals feed much like their modern relatives, extending tiny tentacles to capture small organisms from the water column. But their feeding activities are so gentle and unhurried that they seem more like meditation than predation. The tentacles move with slow, hypnotic grace, creating subtle currents that draw food particles toward the coral's central mouth without any sense of urgency or aggression. Some coral species have developed remarkable adaptations for life in the ancient seas. Certain forms have evolved bioluminescent capabilities, creating soft, pulsing lights that attract prey and communicate with other corals. These living lanterns create an underwater light show that adds an element of magic to the already enchanting trilobite world. The bacterial communities that form the foundation of life in these ancient seas have also evolved into spectacular forms that rival any modern organism in their beauty and complexity. Some bacterial colonies have grown into massive, tower-like structures called stromatolites that rise from the seafloor like underwater skyscrapers. These living monuments are built over thousands of years as successive generations of bacteria secrete calcium carbonate and other minerals, slowly constructing elaborate architectural forms. The stromatolites create their own microenvironments around their bases, with specialized bacterial communities that thrive in the unique chemical and physical conditions created by the towers. These bacterial gardens support diverse communities of small animals, including many types of primitive worms, tiny arthropods, and other microscopic life forms that find shelter and food in the complex three-dimensional habitat created by the bacterial construction activities. Other bacterial communities have evolved into forms that look like underwater carpets or tapestries, with intricate patterns of color and texture that change throughout the day as different bacterial species become active in response to varying light and chemical conditions. These living artworks create some of the most beautiful displays in the ancient seas, with patterns that shift and flow like slow-motion kaleidoscopes. The early mollusks that share the trilobite world represent another fascinating group of ancient animals. These primitive shell-bearers have evolved a variety of forms that exploit different ecological niches in the marine environment. Some have developed coiled shells that they carry like portable homes, allowing them to retreat completely inside when they need protection or rest. These early snail-like creatures move across the seafloor with the same unhurried grace that characterizes all life in the ancient seas. They glide along on muscular feet that leave distinctive trails in the bacterial mats, trails that intersect and overlap with those left by trilobites to create complex patterns that record the movements of the entire seafloor community. Other mollusks have evolved into forms that look like primitive clams, with two shells that can open and close to control their interaction with the surrounding water. These bivalve ancestors spend much of their time buried in the seafloor sediment, extending siphons to the surface to filter food from the water column. Their feeding activities help to circulate water and nutrients through the sediment, creating a more dynamic and productive environment for other organisms. The early brachiopods represent another major group of shell-bearing animals that contribute to the diversity of the trilobite world. These creatures look superficially similar to clams, but they have a completely different internal organization and feeding strategy. Brachiopods use a specialized filtering organ called a lophophore to capture food from the water column, creating delicate currents that draw small organisms and particles toward their feeding apparatus. The shells of brachiopods are often beautifully ornamented with ribs, spines, and other decorative features that serve both functional and aesthetic purposes. These ornaments help to strengthen the shells while also creating complex water flow patterns that enhance feeding efficiency. The result is a group of animals that are both highly functional and extraordinarily beautiful to observe. Swimming among all these bottom-dwelling creatures are the early vertebrates, primitive fish-like animals that represent some of the first attempts at creating complex, mobile organisms with internal skeletons. These early fish are small and simple by modern standards, but they possess a grace and elegance that makes them fascinating to watch as they navigate through their three-dimensional aquatic environment. The early fish have not yet developed the sophisticated swimming abilities that characterize their modern descendants, but they move through the water with a fluid, undulating motion that's perfectly adapted to the calm conditions of the ancient seas. Their movements create gentle pressure waves that can be detected by the sensitive mechanoreceptors of trilobites and other bottom-dwelling animals, adding an acoustic dimension to the communication networks of the seafloor community. Some early fish species have evolved specialized feeding strategies that complement rather than compete with the trilobites and other invertebrates. These fish feed primarily on planktonic organisms in the water column, helping to control populations of small drifting creatures while providing nutrients to the seafloor ecosystem through their waste products. The interactions between all these different groups of organisms create a web of relationships that's incredibly complex and sophisticated. Trilobites serve as ecosystem engineers, modifying the physical structure of the seafloor in ways that create habitat for smaller organisms. The crinoids and other filter feeders help to clarify the water column, making conditions more favorable for photosynthetic bacteria and improving visibility for visually guided organisms like trilobites. The coral animals and other small predators help to control populations of microscopic organisms, preventing any single species from becoming too dominant and maintaining the diversity that characterizes the ancient marine ecosystem. The mollusks and brachiopods contribute to nutrient cycling by filtering and processing large volumes of seawater, concentrating nutrients and making them available to other organisms. Even waste products play important roles in maintaining the balance of the ancient ecosystem. The shells and skeletons of dead organisms provide substrate for bacterial growth and habitat for small animals. The waste products of living animals provide nutrients for bacterial communities and help to maintain the chemical balance of the seawater. The result is an ecosystem that's remarkably stable and self-regulating, with each component contributing to the overall health and productivity of the whole. This stability allows for the long-term evolutionary experiments that have produced such remarkable diversity in the trilobite world, providing a secure foundation that supports innovation and adaptation without threatening the basic integrity of the system. The seasonal rhythms that govern trilobite life also affect all the other organisms in the ancient seas, creating synchronized patterns of activity that enhance the efficiency and stability of the entire ecosystem. During the bright seasons, increased photosynthetic activity by bacteria supports larger populations of filter feeders, which in turn provide more food for predators and more nutrients for the seafloor community. During the quiet seasons, reduced activity levels allow for the healing and regeneration of damaged habitats, the consolidation of evolutionary gains, and the preparation for the next cycle of abundance. The entire ecosystem breathes together, expanding and contracting in harmony with the ancient rhythms that govern life in these primordial seas. As you continue to drift through these ancient waters, suspended in their warm embrace, you gradually become aware that the trilobite world exists within a much larger context of planetary change and transformation. The peaceful seas that have nurtured such incredible diversity are themselves part of a vast, slow-moving dance between ice and water, between cooling and warming, that has been shaping the Earth's climate for millions of years. The signs of this greater dance are subtle at first, barely perceptible changes in water temperature and chemistry that occur over timescales so long that they're almost impossible to detect without the most careful observation. But as you attune yourself to the deeper rhythms of the ancient Earth, you begin to sense the profound forces that are slowly reshaping the planet's climate, and, with it, the destiny of all life in the seas. The water around you carries within it the chemical memory of distant ice sheets, massive accumulations of frozen water that have begun to grow on the far-off continents. These ice sheets are still small by the standards of later ice ages, but they're already large enough to begin affecting the global circulation of water and heat. As more and more water becomes locked up in ice, sea levels begin to drop slowly, exposing new areas of continental shelf while deepening the ocean basins. The gradual cooling that drives ice sheet growth is so gentle that it barely affects the comfortable temperature of the trilobite seas. The water remains perfectly warm and inviting, its temperature dropping by perhaps a degree over the course of thousands of years, so slowly that no individual trilobite would ever notice the change during its lifetime. Yet this subtle cooling is part of a much larger pattern that will eventually transform the entire planet. The trilobites and their companions adapt to these slow changes with the same grace and patience that characterizes all their activities. Species that are particularly sensitive to temperature begin to shift their ranges slightly, following the warmest water to maintain optimal living conditions. Others develop physiological adaptations that allow them to function efficiently across a wider range of temperatures. The ice sheets themselves create their own local climates that begin to influence weather patterns across the entire planet. Cold, dry air flowing off the ice creates high-pressure systems that alter wind patterns and ocean currents. These changes are subtle at first, but they gradually propagate throughout the global climate system, creating new patterns of circulation that will persist for millions of years. The ocean currents that have carried nutrients and warmth throughout the trilobite seas begin to shift in response to the changing pressure systems and temperature gradients. Some currents strengthen while others weaken, creating new patterns of upwelling and downwelling that redistribute nutrients and affect the productivity of different marine regions. These current changes don't disrupt the fundamental stability of the trilobite world, but they do create new opportunities and challenges that drive continued evolution and adaptation. Areas that were once nutrient-poor become enriched by new upwelling patterns, supporting explosive growth in bacterial communities and the trilobites that feed on them. Other areas that were once highly productive become less favorable as currents shift away from them. The trilobites respond to these changes with remarkable flexibility, their mobile lifestyle allowing them to track favorable conditions as they shift across the seafloor. Some species develop enhanced swimming abilities that allow them to follow favorable currents over longer distances. Others become more efficient at extracting nutrients from lower concentration water, adapting to regions where productivity has declined. The changing ice volume on the continents also affects the chemistry of the oceans in subtle but important ways. As more water becomes locked up in ice, the concentration of dissolved minerals in seawater increases slightly. This enhanced mineralization makes it easier for shell-bearing organisms like trilobites to extract the calcium carbonate they need for their exoskeletons, leading to a proliferation of heavily armored species. The increased mineral concentration also affects the bacterial communities that form the base of the marine food web. Some bacterial species that specialize in processing specific minerals become more abundant, while others that prefer more dilute conditions become less common. These changes ripple up through the food web, affecting the types and abundance of food available to trilobites and other marine animals. Sea level changes driven by ice accumulation create some of the most dramatic habitat modifications in the trilobite world. As water becomes locked up in continental ice sheets, vast areas of shallow seafloor are gradually exposed to the air, forcing entire communities of marine organisms to retreat to deeper water. These migrations create opportunities for rapid evolution as populations become concentrated in smaller areas and face new competitive pressures. At the same time, the lowered sea levels create new deep water habitats as ocean basins become more pronounced. These deeper environments offer new ecological niches that trilobites and their companions can exploit, leading to the evolution of specialized deep water forms that are adapted to life in the darker, colder conditions of the abyssal seafloor. The exposed continental shelves don't remain barren for long. Bacterial communities that are adapted to terrestrial conditions begin to colonize these new land areas, creating some of the first substantial terrestrial ecosystems in Earth's history. While these early land communities are still primitive compared to later terrestrial life, they represent an important step in the expansion of life beyond the oceans. The interaction between terrestrial and marine ecosystems begins to create new feedback loops in the global climate system. The bacterial communities on land affect local weather patterns and contribute to rock weathering processes that change the chemistry of rivers and groundwater. These chemical changes eventually reach the oceans, creating new nutrient inputs that affect marine productivity. The ice sheets themselves become habitats for specialized communities of organisms that are adapted to life in frozen environments. While these ice-adapted communities are still simple and limited compared to later polar ecosystems, they represent the first experiments in life at very low temperatures. Some of these organisms develop remarkable adaptations, including antifreeze proteins and metabolic processes that can function at temperatures just above freezing. The margins of the ice sheets, where ice meets water or land, become particularly important as zones of interaction between different climate systems. These boundary regions often experience the most rapid environmental changes as ice advances and retreats, creating strong selective pressures that drive rapid evolution in local populations of organisms. Seasonal patterns become more pronounced as the ice sheets grow larger and begin to exert stronger influences on regional climate. Areas that once experienced relatively stable conditions throughout the year begin to show more distinct seasons as cold air masses from the ice sheets create stronger temperature contrasts. These enhanced seasonal patterns provide new selective pressures that drive the evolution of more sophisticated behavioral and physiological adaptations. The trilobites and their companions develop increasingly complex responses to these enhanced seasonal cycles. Some species evolve the ability to enter dormant states during the coldest periods, reducing their metabolic activity to conserve energy when food is scarce. Others develop migration patterns that allow them to follow optimal conditions as they shift geographically with the seasons. The timing of reproduction becomes more critical as seasonal patterns become more pronounced. Species that can synchronize their reproductive cycles with optimal environmental conditions gain significant advantages over those that reproduce at random times. This leads to the evolution of increasingly sophisticated biological clocks and environmental sensing abilities. Communication systems also become more important as environmental conditions become more variable and unpredictable. Species that can share information about changing conditions, food availability, and environmental hazards are better able to adapt to the increasing variability created by the growing influence of ice on global climate. The chemical composition of the atmosphere begins to change as well, though these changes are subtle and occur over very long timescales. The ice sheets affect the cycling of carbon dioxide and other greenhouse gases, creating feedback loops that influence the rate of climate change. These atmospheric changes have complex effects on marine chemistry and productivity that propagate throughout the ocean ecosystem. Ocean acidification, caused by increased dissolution of carbon dioxide in seawater, begins to affect shell-bearing organisms like trilobites. However, the changes are gradual enough that most species can adapt through evolutionary modifications to their shell chemistry and structure. Some species develop shells that are more resistant to acidic conditions, while others modify their calcification processes to maintain shell strength under changing chemical conditions. The deep ocean begins to change as well, as shifting temperature gradients affect the formation and circulation of deepwater masses. These changes influence the distribution of nutrients and oxygen in the deep sea, creating new environmental conditions that drive the evolution of specialized deepwater communities. Some trilobite species begin to explore these deeper environments, developing adaptations that allow them to survive in the darker, colder, and more nutrient-poor conditions of the deep ocean. These deep-sea pioneers evolve enhanced sensory systems to navigate in the perpetual darkness, more efficient metabolisms to cope with limited food resources, and modified reproductive strategies that can function in the stable but harsh conditions of the abyss. The volcanic activity that continues to shape the ocean floor also interacts with the changing climate system in complex ways. Underwater volcanic eruptions release heat and chemicals that can temporarily warm local areas and provide pulses of nutrients to marine communities. These volcanic inputs become increasingly important as other sources of heat and nutrients are modified by the growing ice sheets. Some volcanic regions become refugia, where trilobites and other marine organisms can survive during particularly harsh climate episodes. These volcanic oases maintain stable, warm conditions even when the surrounding ocean becomes colder and less productive. The organisms that survive in these refugia often serve as the source populations for recolonization when conditions improve. The interplay between ice, water, and volcanic activity creates a complex, dynamic system that is constantly shifting and changing. No two regions of the ocean experience exactly the same sequence of environmental changes, creating a mosaic of different evolutionary pressures and opportunities that drives continued diversification in trilobite communities. As you observe this vast, slow dance of planetary forces, you begin to understand that the trilobite world exists in a state of dynamic equilibrium. The creatures and communities you see around you are not static entities, but rather dynamic systems that are constantly adapting and evolving in response to the ever-changing conditions of their environment. The remarkable stability and longevity of trilobite dominance in the ancient seas is not due to unchanging conditions, but rather to their incredible ability to adapt and respond to change while maintaining the essential characteristics that make them successful. They are master dancers in the great planetary ballet of ice and water, able to adjust their steps to match the changing rhythm while never losing their essential grace and elegance. The warm water that surrounds you carries within it the memory of this ancient dance, the accumulated experience of millions of years of adaptation to slowly changing conditions. In the chemical traces and temperature gradients of the sea, you can sense the vast forces that are shaping the destiny of all life on Earth. Forces that work so slowly and gently that they seem almost benevolent in their patient transformation of the world. As you drift deeper into the flow of geological time, suspended in waters that have witnessed the rise and flourishing of the Trilobite Empire, you begin to sense a subtle change in the rhythm of life around you. The transformation is so gradual that it's barely perceptible at first, like the almost imperceptible shift from late afternoon to early evening. The Trilobites continue their ancient activities with the same grace and purpose that has characterized their existence for hundreds of millions of years. But there's something different in the quality of their world, a gentle melancholy that speaks of approaching change. The first signs of this transformation appear in the diversity of forms around you. While trilobites remain abundant and successful, the incredible explosion of new species and body plans that characterized earlier periods has begun to slow. Evolution continues its patient work, but the pace of innovation has shifted from rapid experimentation to careful refinement of existing designs. The trilobites have become masters of their craft, perfecting adaptations that have served them well for so long that major changes are no longer necessary or advantageous. The water temperature continues its almost imperceptible cooling, dropping perhaps a degree every few million years as ice sheets on distant continents continue their slow but relentless growth. The trilobites adapt to these changes with their characteristic resilience, but the cooling represents the beginning of environmental pressures that will gradually reshape their world in fundamental ways. Sea levels continue their gradual decline as more and more water becomes locked up in continental ice. Vast areas of shallow seafloor that once provided ideal habitat for trilobite communities are slowly exposed to the air, forcing populations to retreat to deeper waters or migrate to more favorable locations. These habitat losses don't create immediate crises, but they gradually reduce the total area available for trilobite colonization and increase competition for the remaining suitable areas. The trilobites respond to these challenges with remarkable adaptability, developing new strategies for making the most of increasingly limited resources. Some species become more efficient at extracting nutrients from their environment, requiring less food to maintain their populations. Others develop enhanced mobility that allows them to track optimal conditions as they shift across the changing seafloor landscape. Despite these adaptations, the overall abundance of trilobites begins a slow, almost imperceptible decline. Individual populations remain healthy and successful, but the total number of trilobites in the world's oceans gradually decreases as available habitat shrinks and environmental conditions become more challenging. This decline is so gradual that it would be invisible to any individual trilobite or even to entire generations. But over millions of years, the trend becomes unmistakable. The changing climate also affects the other organisms that share the trilobite world. Some groups, particularly those that are well adapted to cooler conditions, begin to flourish and diversify. Others, like the trilobites, find themselves gradually squeezed into smaller and smaller ranges as their preferred habitats become less common. New types of predators begin to appear in the ancient seas, creatures that are more mobile and aggressive than the gentle filter feeders and deposit feeders that have dominated marine ecosystems for so long. These new predators don't immediately threaten trilobite populations, but they represent a fundamental shift in the nature of marine life toward more active and competitive interactions. The trilobites develop new defensive strategies in response to these emerging threats. Some species evolve the ability to roll up into tight balls when threatened, protecting their soft undersides with their hard dorsal shells. Others develop spines and other defensive structures that make them more difficult for predators to handle. Still others enhance their burrowing abilities, creating deeper and more secure refuges in the seafloor sediment. But perhaps more significant than any specific adaptation is the way that trilobites begin to change their overall lifestyle in response to the more challenging world around them. The open, exploratory behavior that characterized earlier trilobites gradually gives way to more cautious and conservative approaches to survival. Trilobites spend more time in burrows and other protected locations, venture less far from safety, and become more selective about their activities and movements. This shift toward caution and conservation has profound effects on trilobite evolution and behavior. Innovation becomes less common as populations focus on perfecting tried-and-true survival strategies rather than experimenting with new approaches. Social structures become more rigid and hierarchical as competition for resources increases. Communication systems become more focused on warning and defense rather than cooperation and resource sharing. The changing chemistry of the oceans also plays a role in the gradual transformation of the trilobite world. As atmospheric composition shifts in response to changing climate conditions, the chemistry of seawater changes as well. Some changes favor trilobite survival, while others create new challenges that require evolutionary responses. Ocean acidification, caused by increased dissolution of carbon dioxide in seawater, begins to affect the ability of trilobites to maintain their calcium carbonate shells. While most species can adapt to these changes, the energy cost of shell maintenance gradually increases, leaving less energy available for growth, reproduction, and other activities. The availability of trace nutrients also changes as ocean circulation patterns shift in response to changing climate conditions. Some nutrients become more scarce, while others become more abundant. These changes require adjustments in trilobite metabolism and feeding strategies, adding another layer of evolutionary pressure to an already challenging environment. Despite all these challenges, trilobites continue to demonstrate the remarkable resilience and adaptability that has allowed them to survive and flourish for so long. New species continue to evolve, exploiting whatever opportunities remain available in the changing world. Some lineages develop highly specialized adaptations that allow them to thrive in specific environmental niches that other organisms cannot exploit. The deep ocean becomes increasingly important as a refuge for trilobite diversity. As shallow habitats become less favorable, more and more trilobite species adapt to life in the deeper, more stable conditions of the abyssal seafloor. These deep-sea trilobites evolve remarkable adaptations for life in perpetual darkness, including enhanced sensory systems and highly efficient metabolisms. Some of the most beautiful and elaborate trilobite forms evolve during this period of gradual decline. As if responding to the increasing challenges of their world with an outpouring of creativity, evolution produces trilobites with incredibly complex eye systems, bizarre and ornate shell decorations, and specialized appendages that represent the ultimate refinement of arthropod design. These late evolving trilobites are like the final masterpieces of a great artist, representing the culmination of hundreds of millions of years of evolutionary experimentation and refinement. They achieve levels of complexity and sophistication that rival or exceed anything that evolution has produced before or since. Yet they do so in a world that is gradually becoming less hospitable to their way of life. The social structures of trilobite communities also reach new levels of sophistication during this period. Some species develop complex cooperative behaviors that allow them to survive in increasingly challenging environments. Others evolve elaborate communication systems that help coordinate group activities and share information about environmental conditions and resources. Reproductive strategies become more sophisticated as well, with many species developing enhanced parental care behaviors and more precise timing of reproductive activities. Some trilobites begin to show evidence of what might be called cultural transmission, with learned behaviors being passed from generation to generation through social interaction rather than genetic inheritance. As environmental pressures continue to mount, some trilobite populations become increasingly isolated from each other, leading to the development of distinct regional populations with unique adaptations and characteristics. This geographic fragmentation of trilobite communities contributes to continued speciation and diversification, even as the overall number of trilobites in the world continues its gradual decline. The quality of life in trilobite communities remains high despite the increasing challenges. The fundamental peacefulness and cooperation that has always characterized trilobite society continues to provide a stable foundation for their communities. Individuals continue to follow the ancient rhythms of feeding, molting, mating, and social interaction that have sustained their kind for so long. Seasonal patterns continue to govern trilobite life, though these patterns gradually become more pronounced as climate changes create stronger seasonal contrasts. The bright seasons become shorter and less intense, while the quiet seasons become longer and more challenging. Trilobites adapt their behaviors accordingly, developing more elaborate strategies for surviving the difficult periods and making the most of favorable conditions when they occur. The long twilight of trilobite dominance is marked not by sudden catastrophe or dramatic extinction events, but by the gradual accumulation of small challenges and subtle changes that slowly tip the balance of survival in favor of other groups of organisms. It's a process that unfolds over tens of millions of years, so slowly that no individual trilobite or trilobite community experiences it as a crisis or emergency. As you float in these ancient waters, watching the gentle decline of the trilobite world, you begin to understand that you are witnessing not just the end of an era, but the beginning of a legacy that will persist far beyond the lives of these remarkable creatures. The trilobites may be slowly fading from the seas that have been their home for so long, but their influence on the world will continue in ways that they could never imagine. The shells and exoskeletons that trilobites shed throughout their lives are beginning to accumulate in vast deposits on the seafloor, creating the first extensive fossil record in Earth's history. Each molted shell, each deceased individual, becomes a time capsule that preserves not just the physical form of the creature, but also information about the environment in which it lived, the food it ate, and the conditions that shaped its existence. These accumulating fossils are like pages in an enormous book that is being written by the trilobites themselves, a book that will eventually tell their story to creatures that have not yet evolved, in worlds that have not yet been imagined. The calcium carbonate of their shells slowly transforms into stone, preserving their intricate structures in perfect detail for hundreds of millions of years. The process of fossilization is itself a gentle one, matching the peaceful character of trilobite life. As each shell settles into the seafloor sediment, it is gradually covered by layers of fine particles that protect it from destruction. Over time, mineral-rich water percolates through these sediment layers, slowly replacing the original shell material with more durable minerals while preserving every detail of the original structure. Some fossils preserve not just the hard shells of trilobites, but also evidence of their soft tissues, their behavior, and their interactions with other organisms. Trace fossils capture the tracks and trails left by trilobites as they moved across the ancient seafloor, preserving evidence of their feeding patterns, their social behaviors, and their responses to environmental changes. The most remarkable fossils preserve entire trilobite communities in perfect detail, creating windows into ancient ecosystems that allow future scientists to reconstruct the complex relationships between trilobites and their environment. These fossil assemblages capture moments in time when conditions were just right for exceptional preservation, creating natural museums that will survive for geological ages. As the trilobite world slowly transforms, other groups of organisms begin to rise to prominence, building on the foundation that trilobites have created, but adding their own innovations and adaptations. Fish become more diverse and sophisticated, developing new swimming abilities and feeding strategies that allow them to exploit resources that trilobites cannot access. New types of arthropods evolve, some of which will eventually leave the water entirely and colonize the land. These terrestrial pioneers carry with them the genetic and morphological heritage of their trilobite ancestors, adapting the basic arthropod body plan to the challenges of life in air rather than water. The ecological relationships that trilobites have established continue to influence marine ecosystems long after trilobite diversity begins to decline. The bioturbation patterns created by trilobite burrowing activities persist in the seafloor, affecting sediment chemistry and water circulation for millions of years. The feeding strategies pioneered by trilobites are adopted and refined by other organisms, creating continuity in ecosystem function even as the specific organisms involve change. The evolutionary innovations that trilobites developed during their long reign in the seas become part of the genetic toolkit that life will draw upon for future experiments. The compound eyes of trilobites represent one of the most sophisticated visual systems ever evolved, and their basic design will be preserved and modified in countless other arthropod lineages. The segmented body plan that allowed trilobites to achieve such remarkable diversity becomes the foundation for all future arthropod evolution. Insects, spiders, crustaceans, and countless other arthropod groups will build upon the basic trilobite design, creating new variations that will eventually colonize every habitat on Earth. The social behaviors and communication systems that trilobites developed continue to influence the evolution of animal behavior long after the last trilobite disappears from the seas. The chemical communication systems, territorial behaviors, and cooperative feeding strategies that characterize trilobite communities provide templates that other organisms will adopt and modify for their own uses. Even the timing of trilobite extinction contributes to the legacy they leave behind. By gradually declining rather than disappearing suddenly, trilobites provide time for other organisms to adapt to their absence and to develop new ways of filling the ecological roles that trilobites once occupied. This gradual transition helps to maintain ecosystem stability and prevents the collapse of marine communities. The sedimentary rocks that form from trilobite-bearing seafloor deposits will eventually be uplifted and exposed on land, where they will weather and erode to release nutrients that will support terrestrial ecosystems. In this way, the trilobites will literally become part of the foundation that supports future life on land. The fossils that preserve trilobite remains will eventually be discovered by curious humans who will piece together the story of these ancient creatures and their world. Through careful study of trilobite fossils, scientists will learn about evolution, ecology, behavior, and climate change in ways that would be impossible without the detailed record that trilobites have left behind. The beauty and complexity of trilobite fossils will inspire artists, writers, and philosophers, contributing to human culture and creativity in ways that span far beyond their scientific importance. The intricate patterns of their eyes, the graceful curves of their shells, and the elegant symmetry of their body plans will serve as models for human artistic expression. Children will hold trilobite fossils in their hands and wonder about the ancient world in which these creatures lived, sparking curiosity and imagination that will lead some of them to become scientists, artists, or explorers themselves. In this way, trilobites will continue to influence and inspire life on Earth long after their own extinction. The climate changes that contribute to trilobite decline will eventually reverse, as the ice sheets that have been growing for so long begin to melt and retreat. When warmer conditions return to the seas, other organisms will take advantage of the opportunities that trilobites once exploited, but they will do so in a world that has been shaped by hundreds of millions of years of trilobite activity. The knowledge that trilobites gained about living in marine environments, how to extract nutrients from seawater, how to build protective shells, how to navigate using compound eyes, how to communicate chemically, becomes part of the accumulated wisdom of life on Earth. This knowledge is preserved not just in fossils, but in the genetic heritage of all the organisms that descend from trilobite ancestors or that evolved in trilobite-dominated ecosystems. As you float here in these ancient waters, watching the gentle activities of creatures that represent one of evolution's greatest success stories, you begin to understand that endings and beginnings are really just different aspects of the same continuous process. The trilobites are not truly disappearing. They are transforming, becoming part of something larger and more enduring than any individual species or ecosystem. Their atoms will become part of new organisms. Their genes will contribute to new evolutionary experiments. Their innovations will inspire new adaptations, and their story will become part of the grand narrative of life on Earth. In the warm, nurturing waters that have supported them for so long, trilobites are not dying. They are becoming eternal. The gentle currents that carry you through this ancient sea are the same currents that will eventually carry trilobite nutrients to support other forms of life. The sunlight that filters down through the crystal-clear water is the same sunlight that will warm future oceans and support future ecosystems. The chemical cycles that sustain trilobite life are the same cycles that will sustain all future life on Earth. As you drift deeper into the peaceful embrace of these primordial waters, surrounded by the quiet activities of some of the most remarkable creatures that have ever lived, you can feel yourself becoming part of their story, part of the eternal dance of life that connects all living things across time and space. The trilobites may be approaching their twilight, but their legacy is just beginning, and it will continue to unfold in ways both beautiful and profound for as long as life exists on this planet. Let yourself sink deeper into these warm, ancient waters, feeling the gentle rhythms of trilobite life washing over you like a lullaby from the depths of time. Allow the peace and wisdom of these ancient seas to fill your mind and body, carrying you into dreams of underwater gardens and living jewels, of compound eyes that sparkled in primordial sunlight, and of shells that gleamed like polished bronze in the eternal twilight of the deep. Rest now in the knowledge that you have witnessed one of the most beautiful chapters in the story of life on Earth, and that the echoes of what you have seen will continue to resonate through your dreams and into your waking life, reminding you always of the incredible diversity, resilience, and beauty that life can achieve given enough time and the right conditions. The trilobites continue their ancient dance around you, unhurried and peaceful, following rhythms that are older than mountains and more enduring than continents. Let their patient grace carry you into sleep, knowing that somewhere in the deep memory of life itself, these remarkable creatures continue their eternal journey through the warm, welcoming waters of time.